Okay, let's begin with chapter 5 questions. Find the area of the shaded region. The graph depicts the standard normal distribution. So we want the area to the left of 0.67. That is a normal CDF. And the lower bound, as you can see, it's negative a million. Then the upper bound is 0.67 and 0.1. You paste it, you get the normal CDF, and that's the answer. He wants the answer rounded to 4 decimal places, so that will be 0.7486. Next question. Find the area, as you can notice, between negative 2.33 and 0. So if I bring the calculator back, it will be normal CDF. And the only I think I need to change here is the lower bound will be negative 2.33. And this one will be 0. And then 0.1. And 4 decimal places will be 0.4901. Next question. Find the indicated area between 0 and 0.56. It's exactly the same as the previous one. Normal CDF, so between 0 and the other value is 0.56. You put the lower value first and then the upper value, the larger value, and that's the answer. Next question. The standardized exam scores are normally distributed. In a recent year, the mean test score was 1484 and the standard deviation was 316. The test scores for 4 students selected at random are 1890, 1230, 2170, and 1360. Change them to z-scores. So what's the formula for the z-score? Here's how we do it. So we'll just put the fraction here. The value, which is 1890, minus the mean, which is 1484. And then you divide by you divide by the standard deviation, which is 318. And you do the same thing for the remaining ones. That will be, put the fraction sign. Well, actually, you need to do the calculations. Just make sure that you do the calculations here. 1230 minus, I'm just showing you the work, 1484. And then standard deviation, which is 318. Let's see what these two are. So I'm going to clear this screen. 1890 minus 1484. Let's see what this one is first. I have to do the numerator first and then divide by 318. So your score is 1.28. You just enter 1.28 rounded to 2 decimal places, and you do the same for the rest of them. He's asking you if any of the values are unusual. A value will be unusual if the z-score is more than 2 or less than negative 2. So if you get any answers that are more than 2 or less than negative 2, then they are unusual. Next question. Find the area to the right of negative 1.13. So it is a normal CDF. Let me just bring the calculator. The lower bound is negative 1.13. The upper bound is the sky is the limit, and 0.1. And you get 0.8708. As you can see, it's more than 50%. Next. Assume that the random variable x is normally distributed with a mean of 89 and standard deviation of 4. Find the indicated probability. Again, it's a normal CDF. So let me just bring it down. So we need probability of x less than 85. So there will be second and variables. normal CDF. Okay, less than 85, so negative a million. Put as many zeros as you want here. Put 85. Put the mean now, not 0 and 1, because you're working with X, not Z now. So it's 89. And then 4.1587. Next question. In a recent study on world happiness, participants were asked to evaluate their current lives on a scale from 0 to 10, where 0 represents the worst possible life and 10 represents the best possible. The responses were normally distributed with a mean of 5.4 and standard deviation of 2.3. Answer the following question. What is the probability that randomly selected study response was less than 4? So again, it's normal CDF. So you go to second, variables, normal CDF, and then less than 4, so negative a million, that's good, and then you put a 4, then you put the mean, which is 5.4, let me just show that, then you put the standard, let's just go back and make sure that I put this right, and standard deviation is 2.3. 2.3. Okay, and then paste. So, and you get the answer 0.2714. Second question, what's the probability random selected study participants response was between 4 and 6? So it's second and variables, normal CDF, and lower is 4, upper is 6, and the mean and the standard deviation remain the same. There you go. Next question. Probability if randomly selected participants was more than 8. That's a low probability here. More than 8, so you start with 8 as a lower. Upper will be a million, and leave the mean and standard deviation alone, and it's 1.1291. Identify any unusual events. If any of the probabilities are less than 5%, they are considered unusual events, but as you notice, none of them are less than 5%, so there are no unusual events in here. Okay, next question. Very much similar question. In a recent year, the total score of a certain standardized test were normally distributed with a mean of 500, standard deviation of 10.7. Find the probability randomly selected medical students who took the test had a total score that was less than 492. Okay, so we just come here, second, variables, normal CDF, less than 492, so negative a million, 492, mean is 500, and standard deviation, as you noticed, it's 10.7. And there you go, that's the answer, 2273. Next question. Find the probability randomly selected medical students who took the test at a total score that was between 495 and 507. The between is easy. You just change this one to 495 and then 507. Paste, and that's the answer. C. Find the probability randomly selected medical students who took the test at a total score that was more than 523. This is the MCAT. It's unusual to have someone get 523. So let's see. So 523, and then a million. So 1.6 6% of students who take the MCAT get a high score, 523. Okay. So next, identify any unusual event. The answer in part C is unusual because it's less than 5%. So I'll choose A here. Okay. And then move on. Use a normal distribution of set critical reading score for which the mean is 509 and the standard deviation is 120. Assume the variable x is randomly normally distributed. What percent of set scores are less than 500? It's the same thing as the probability of x less than 550. So just normal CDF, second, and distribute. Normal CDF, negative a million, 550. The mean is 509 and standard deviation is 120. Paste. So 0.6337. If 1000 set verbal scores are randomly selected, about how many would you expect to be greater than 525? Before we know how many, we need to find the probability that x will be greater than 525. So we go second, variables, normal CDF. I need probability of x greater than 525. So put 525 and then a million. And then paste. That's a probability. Now we have 1,000 of them. How many will have a score of greater than 525? Just multiply this answer by 1,000. And we need to round to the nearest whole number, so it will be 447. Okay. Next. Find the indicated z-score. Now he gives you the area and wants the z-score. It's an inverse norm now. The area to the left is 0, and you need the area to the left. So you just go to second, variable, inverse norm, 0.117, and then 0.1. Why 0.1? Because that's a z. So it's negative 1.19. Next. Find the indicated z-score. Second, normal inverse norm. Since this area is area to the left, so I need 1 minus 0.0505 and 0.1 again. And here you go, it's 1.64. Next. The undergraduate grade point average of students taking an admission test in a recent year can be approximated by normal distribution. It's given us the mean and the standard deviation, as you can see. What is the minimum UGPA that will still place someone at the top 10%? Top 10% will be an area to the right, and since the inverse norm requires an area to the left, so we need 90%. So you just go second, variables, inverse norm, 0.9, and mean is, you don't put 0.1 here, he wants the x value, so 0.32, we already have a mean and a standard deviation, 0.19, 3.56. Between what two values does the middle 50% of the UGPA lies? Okay, middle 50%, so you put a 50% right in the middle, then you're gonna get on the tail a 25% and a 25%. So you do the inverse norm on the first 25%. That will give you the first middle value, 0.25, and enter, paste, 3.19. The second one will be the complement of 25%, which is 75%, because they add up to 100%. So you just go second. I'm gonna go second and enter, and I'm just gonna change the 25 to 75. So again, this number and that number will add up to 100%. So this is how you do the middle again. If he says middle 80%, you subtract the 80% from 100, you get 20%, divided by 2, you get 10%. So you do inverse norm on 10% and you do inverse norm on 90%. And here is the other answer, 3.45. The pregnancy length in days for a population of new mothers can be approximated by a normal distribution with a mean of 265 and a standard deviation of 11. What is the minimum pregnancy length that can be in the top 11%? So top 11% means 11% is on the right, and the inverse norm requires an area on the left. So if it is 11% on the right, what would it be on the left? It will be 100% minus 11%, 89%, 0.89. Don't put 89, just make it as a decimal. And what's the mean and the standard deviation? 265 and 11. So it will be 278 days. It says round to one decimal, so 278.5, as you can see right here. What's the maximum pregnancy length that can be at the bottom 7%? Bottom 7%, that means the 7% is on the left, so you just use the inverse norm with 7%. 0.07. 248.8 days. Okay, that's the answer. Next. Population has a mean of 83 and standard deviation of 25. Find the mean and standard deviation of the sample and distribution. Central limit theorem tells us that the mean of the sample mean is the same as the mean, which is 83. And the standard deviation of the sample mean is the original standard deviation, 25, divided by the square root of the sample size. But don't put it like that as an answer when you do your work. You need to find the answer. He says round it to 3 decimal places. The graph of the annual snowfall distribution in feet for a particular county is shown below on the left, with its mean and standard deviation. Assume the sample size of 225 is drawn from this population. Determine which of the graphs labeled A to C would be most closely resemble the sample and distribution. The mean should be the same as the mean, 4.1, so you have to look for a curve that has a 4.1. It looks like all of them has, except for this one. So this one is a 4.1, this one, that looks like closer. Now the standard deviation has to be 4.1 divided by square root of 225. So let's see, 4.1 square root of 225 is 15, so I'm just gonna divide by 15. So 0.27, that's the standard deviation. You know, to the end of the curve you go 0.27, 0.27, 0.27, 3 standard deviation to the right and 3 standard deviation to the left. It looks like A gives up, because if you add to 4.1 a 0.27, 0.27, 0.27, you'll get almost to 5, and you can see it's almost ends at 5, but here no, it goes all the way to 10. That is the answer. So the graph must closely resemble the sample distribution of the sample mean, because mu of x bar is 4.1 and the standard deviation is 0.27. How many decimals he says, and the graph approximate the normal curve, and then you move. The heights of fully grown trees of a specific species are normally distributed with a mean of 74 and standard deviation of 5.75 feet. Random samples of size 19. Now we're not picking one individual, we have samples, so it's a central limit theorem. Use the central limit theorem to find the mean and the standard error. The mean will be the same as 74. The standard error, guys, will be 5.75. divided by the square root of the sample size, which is 19 here. You do the math and figure out the answer. Choose the graph that resamples this. If I do 5.75 divided by square root, let's see what the standard deviation is. (1.31). So you need 74 and then 1.31 added 3 times and subtracted 3 times. It looks like A. If you add 1.3 3 times, will give you another 4. Yeah, that's 1, 2. That's a 75.6. Yeah, 75.4, 76. That makes sense. So it is A. The mean height of women in a country is 64.4 inches. A random sample of 55 women in the age group is selected. What's the probability that the mean height for the sample is greater than 65? Now it's not a probability of X, guys, it's probability of X bar greater than 65. And sigma is 2.53. So here's how you answer this question. Second, and distribution variable, normal CDF, more than 65. So 65 is the lower bound. Million is the upper bound. Mean is, what did he say the mean? 64.4. Standard deviation, it's not 2.53, it's 2.53 divided by the square root of the sample size, which is square root of 55. Don't forget that. And now you're gonna get the right answer because it's a probability of X bar greater than 65. Will be 0.0393. The heights of women aged 2020 is normally distributed with a mean of 63.8. Assume sigma is 2.7. Are you more likely to randomly select one woman with the height of less than 65.7 inches, or are you more likely to select a sample of 16 women with a mean height less than 65.7? Well, it's asking us to find the probability, in other words. Now, one person is just probability of X. So for the first one will be normal CDF, less, so negative a million, 65.7 inches, and then you put the mean and the standard deviation, 63.8, and then the standard deviation, which is what did he say? The standard deviation 2.7. You do this. Now, what's the probability that selecting a sample of 16 women with height less than 65.7? It will be normal CDF, and then negative a million, comma 65.7, and then the mean is 63.8. Look what's gonna change now. The standard deviation is 2.7 divided by square root of 16, which is, we know it's 4. Then you do both ones. The one that has higher probability is the more likely one to happen. Okay. Okay, I'm gonna stop here and do a different video for chapter 6. That is the end of chapter 5 review.